Summer 2019, Paper 2, Calculator. So I've got all my equipment just the same as in Paper 1, but I've also got my calculator sitting here ready. I've set it up so it's working, I've checked it, everything's okay to start, so let's have a go at the paper. Question 1. Write 0.75 as a fraction. Well, there's a couple of different ways we could do this. 0.75, we might want to recognise that that is, for example, 75 over 100. It's the same as 75%, which means it must be the same as 75 over 100. We could then cancel that down. There's a couple of different things we could cancel it down by, but you might notice that it will cancel down by 25. It's quite a tricky spot, but it is possible to do. 75 divided by 25 is 3, 100 divided by 25 is 4, and we would get 3/4. Alternatively, you might just recognise that 0.75 is one of those standard decimals that it's useful to know the fraction conversion for, and you might recognise that 0.75 is the same as 3/4 and be able to just write it down straight away. Question 2. Write the following numbers in order of size. Start with the smallest number. And then we've got -3, 4, 0, -1 and 2. You could draw yourself a quick number line, perhaps you already have somewhere on the paper. You could draw yourself a quick number line if you like, to help you, to remind you, or you might just jump in and recognise that on the left hand side of the number line, below the 0, we're going to start with the -3, then we're going to get a bit bigger to the -1, and then hit the 0, then the 2, and then the 4. But if you want to draw yourself a number line, it might be a useful thing. It's always something you could come back to later on in the paper if you need it. Question 3. Write down 2 factors of 15. Factors, remember, things that a number will divide by. So we want to write down 2 things that 15 will divide by. Any 2 will work, but you could either choose from 1 and 15, or you could choose 3 and 5, because 1 times 15 is 15, and 3 times 5 is 15. So any 2 of 1, 3, 5 and 15. It doesn't say you have to write down a pair, so you could have 1 and 3, you could have 3 and 15, say. It would make more sense to write them down as a pair, but any of those will do. Any 2 of those 4. Question 4. Change 1,756 grams to kilograms. Well, we're talking about grams and kilograms, so it might be helpful to write down the fact that we know about grams and kilograms. That 1,000 grams is the same as 1 kilogram. From there, it might also be useful to write down that 2,000 grams then, if 1,000 grams is 1 kilogram, then 2,000 grams will be 2 kilograms. 1,756 falls between 1,000 and 2,000. So the conversion to kilograms will fall between 1 and 2. We need a number between 1 and 2 that keeps all of the information from this. It keeps the same digits, the 1, the 7, the 5 and the 6, in that order. We need a number between 1 and 2. So we must be saying that it is 1.756 kilograms. By adding in the point to there, we're keeping all the numerical information. We're keeping the 1, the 7, the 5 and the 6 in that order. But we're adding the point in to scale it so it's between 1 and 2. Question 5. Write the number 2 million in figures. Well, it might be helpful if you need to draw yourself a hundreds, tens and units grid so that you can make sure you've got in particular the right number of zeros. So we can start with the units, tens, hundreds, thousands, 10,000s, 100,000s, and then millions. We need 2 million, so we're going to have to put a 2 in the millions, and then we're going to have to fill up the other columns with zeros down to the end of the units, because that's where the decimal point would go if we were moving into a decimal number. So we're going to need 1, 2, 3, 4, 5, 6 zeros. 2, and then 6 zeros. 2 million. Question 6. Dave goes into a cafe and buys 2 cups of coffee and a piece of cake. Each cup of coffee is £2.75. The cake costs £2.90. Dave pays with a £10 note. He thinks he will get more than £1.50 in change. Is Dave correct? You must show how you got your answer. Right, well, to work out whether Dave is correct, we need to know whether he will get more than £1.50 in change or whether he won't. If he does, then yes, he is. If he doesn't, then no, he isn't. So to check whether he's right or not, we need to work out probably how much change he would get from the £10 note. To work out change, of course, change is the amount that you hand over, less the amount that your shopping comes to. So there's our first step. We need to work out the cost of the shopping. 2 cups of coffee and a piece of cake. Each cup of coffee is £2.75, so we've got £2.75 plus the £2.75 plus the £2.90 for the piece of cake. Notice that even though this is a calculator paper and I'm going to put this in my calculator to work out the answer to this, I am still writing it down. We need to show the examiner that this is the sum that we're doing. On the non-calculator paper, we would probably have gone off to the side and maybe written this as a column addition perhaps, so that we could work out the answer. Here, we don't need to do that. We don't need to show how we've done the addition, but we do need to show that we have done it. We need to write down the question that we have put into our calculator. So I can then put these things into my calculator, and I'm going to find that that comes to a grand total of £8.40. I'm going to keep the pound sign so that we can keep track of what each number is all the way through. I need to work out the change now. So the change is going to be £10 less the £8.40. Again, I can do that on my calculator, and it would come to £1.60. Notice that I'm also writing down a couple of words here and there just to keep track of what the working is, so that if an examiner looks at our question, or in fact if we look back at it later, we know what we've done. It'll be easier to check your answers if you've kept them fairly organised and labelled things. You don't need to write reams, just the odd word here and there so that you can keep track of what the different numbers mean. Step 3, then we have to answer the question. The question is Dave correct? Well, Dave thinks he will get more than £1.50 in change. He gets £1.60, so yes, Dave is correct. And to get the 3 marks, you need to have that yes, Dave is correct, backed up by the £1.60 that's come from some working out. Question 7. There are Y boats on a lake. Y, remember, algebra coding for a particular number. We don't know what number Y is, but we do know it is a number. There are Y boats on a lake. There are 7 people in each boat. Write an expression in terms of Y for the total number of people in the boats. Okay, expression, piece of algebra that's not particularly equal to anything. It doesn't need to be equal to a number, but it does need to have Y in it somewhere because it needs to be in terms of Y. That means that our algebra expression must contain Y somewhere. It must contain the letter Y. As with a lot of these write an expression or write an equation questions, it can be helpful to think of it first of all in terms of numbers, model a couple of examples with numbers, different values, get the idea of what's going on, and then stretch it out to include the algebra. So imagine we had one boat. One boat would be 7 people. 2 boats. Well, the total number of people in 2 boats would be 2 lots of 7 people, would be 14 people. 3 boats. 3 lots of 7 people. 21 people. 4 boats. 4 lots of 7 people. 28 people. 1 lot of 7, 2 lots of 7, 3 lots of 7, 4 lots of 7. So if we had Y boats, well, 1 boat is 1 lot of 7, 2 boats is 2 lots of 7, 3 boats is 3 lots of 7, 4 boats is 4 lots of 7, so Y boats will be Y lots of 7. Now, there's not much we can do to work anything out there, but we certainly can write that in a better way. We can simplify it using these rules of algebra. We're probably going to want to put the number first, because we tend to put the number first and then the letter, and we can drop out the times sign because it doesn't really need to be there. So in fact, our expression can just be 7y, because y times 7 or 7 times y would be written as 7y. Sticking with the algebra a little bit for question 8, part A. Simplify A times B times 7. Well, very similar to what we've just said for question 7. We need to use the rules of algebra to simplify that, to write it in another form so it still means the same thing but looks a little bit neater. We can get rid of anything we don't need, we write it in the proper way. First thing we're going to do, we're going to move the 7 to the front because we tend to write numbers first and then the letters. It's just a stylistic thing. So we're going to start off with the 7. The times though, do they need to be there? Well, no, they don't, because whenever we have a letter next to a number, whenever we have two letters next to each other, we can drop out the times in the middle and just write them next to each other. So we can simply write that as 7AB. 7BA would also be okay, but we tend to go for alphabetical order because it just looks a little bit neater. But 7BA would also be acceptable. Part B, simplify y times y times y, not 3y. Be very careful. 3y would be the same as y plus y plus y. This is y times y times y. We've taken something, we've taken a number, being coded for by a particular letter, we've times it by itself and then times it by itself again. So in simplifying, what we've done is we've done y to the power of 3. Y cubed, if you like. Part C, simplify fully. E times E times E times F, all divided by E times F times F. Easier than it looks, this. Remember that E and F are particular numbers. We don't know what they are, we'll never know what they are, but they are particular numbers. Let's look first of all at this F at the end here and this F at the end here. On the top, this E times E is a particular number, and then we're timesing that by F. And then on the bottom, we're also doing a divide by F. We've got a particular number times F. Imagine taking something, timesing it by 2, and then immediately dividing it by 2. They are having no net effect. There's no change. Times something by 10, immediately divide it by 10, no net effect, no change. So they might as well not be there. Now what we can do is we can look for stuff that's on the top and on the bottom. We could notice that on the top, we have got an E times F, and on the bottom we've got an E times F. They're in different places, but that doesn't matter. They are there on the top and they are there on the bottom. Now whatever E and F are, E times F comes to a particular number. It has a certain value. And on the top we are taking something and timesing it by the value in that pink box. And on the bottom we are taking something else and timesing it by the value in that pink box. That means that we are doing times by the value in the pink box and then immediately divide by the value in that pink box because of that line in the middle there, that divide line. If we are timesing by the value in the pink box and then dividing by the value in the pink box is having no net effect. It's exactly the same as the times by 2, then immediately divide by 2. They're having no net effect, and if they're having no net effect, then we can ignore them. We can get rid of them. We can cross them off. All we're left with on the top then is an E, and all we're left with on the bottom then is an F. So we've simplified it to E over F. Question 9. The pictogram shows information about the number of vinyl records sold in a shop on Monday and on Tuesday. So we've got Monday, Tuesday, and then Wednesday and Thursday. We've got a key off to the side showing us that the circle represents 8 vinyl records. Part A. Write down the number of vinyl records sold, first of all, on Monday. Okay, so from the key, the circle is 8 vinyl records. So on Monday we've got 1, 2, 3 sets of the circle, which would be 8, 16, 24 vinyl records. And part 2 on Tuesday. So on Tuesday we've got 8, another 8, that's 16, and then a quarter of a circle. If the full circle is 8, a quarter of the circle must be 2. So 8 and 8 is 16, 17, 18 vinyl records sold on Tuesday. On Wednesday and Thursday, a total of 36 vinyl records were sold. The number of records sold on Thursday was 8 times the number of records sold on Wednesday. Use this information to complete the pictogram. So we know that the number of records sold on Wednesday and Thursday in total is 36. And we also know that however big Wednesday is, Thursday is 8 times bigger. So why don't we just test out some values? Imagine that on Wednesday we sold 1 record. On Thursday we sold 8 times more. So we sold 8 records. Do they add up to 36? No, they don't. So maybe we sold 2 on Wednesday. Thursday then we'd have sold 8 more, we'd have sold 16. Do they add up to 36? No, they don't. So maybe we sold 3 on Wednesday. Which means on Thursday we'll sell 8 times more. So we'll sell 24. 3 and 24 comes to 27. Well, that's not 36 either, but we are getting closer. So maybe we're going to be okay with the next one. Maybe we sold 4 on Wednesday. On Thursday we'd have sold 8 times more. So we'd have sold 32. This is looking more promising. 4 on Wednesday, 32 on Thursday. That does indeed come to 36. So we know we sold 4 on Wednesday and 32 on Thursday. That's not that question finished though, because we need to complete the pictogram. So on Wednesday we need to show 4 records being sold. Well, if the full circle is 8, we need to show 4, so we're going to draw half a circle. So there's half a circle for the Wednesday. Thursday we need to show 32. So we're going to need a full circle of 8 and another one that'll take us to 16, 24, 32. Question 10. Here are 3 symbols. So we've got 2 inequality symbols and then we've got an equals. Write one of these symbols in each box to make 4 statements. So that you notice, we've got 3 symbols and 4 boxes, so we are probably going to have to use them more than once. There's also nothing that says we have to use all of the symbols. We might well use all 3 somewhere, but we might not. With the inequality signs, we need to remember which way round they go. We need to remember either that the inequality sign points towards the smaller one, or that the inequality sign is a little bit like a crocodile's mouth and it prefers to eat the larger meal, the larger number. Whichever way around you want to remember it is completely up to you, but we need to recognise that one of those things is going to come into play. So the first one, we have 14 and we have 21. We need to show somehow probably that 14 is smaller than 21. They're clearly not equals and 14 is not bigger. We need to have 21 being the bigger one, 14 being the smaller one. So we need to choose our inequality sign so that either the crocodile is eating the 21 or that the 14 is being pointed to. So we need to have this one here, 14 is less than 21. Second one, 4 plus 7 and 103 minus 92. It would be helpful probably to work those out. We could even do that on a calculator. 4 plus 7 is 11 and 103 minus 92 is also 11. They are in fact exactly the same. And if they're exactly the same, we can use the equals for that one. Third one, we've got 2 squared on one side and 2 times 2 on the other. Well, 2 squared, hopefully we recognise that squaring something is the same as timesing it by itself. So 2 squared would in fact be 2 times 2. We don't particularly need to work out an answer for that. They are actually just different ways of writing exactly the same thing, so we can say that they are also equal. And the final one, minus 3 and minus 5. Well, think about a number line. If there is a 0, minus 1, minus 2, minus 3, minus 4, minus 5. The minus 5 is further down the number line than the minus 3. So the minus 5 is smaller. We need to have some way of using these symbols to show that the minus 5 is smaller. We need to have the minus 3 being the bigger number. So we need to have our arrow pointing towards the smaller one, or we need to have the open mouth of the crocodile at the minus 3. So minus 3 is bigger than minus 5. Question 11. P equals 7r plus 3q. Work out the value of P when r equals 5 and q equals minus 4. Substitution question here doesn't mention the word substitution, but it's clear that that's what it is. We're given an equation to work out P that involves r and q, and we're given the values of r and q. Asked to do certain things with them to find this value of P. We could take this one step at a time. So first of all, we could work out the 7r. Well, if r is 5, then 7r is 7 lots of r. There is a times hidden in between the 7 and the r, so we need 7 times 5 is 35. The 3q now. Well, if q is minus 4, 3q is 3 lots of q, so 3 times the minus 4. 3 times minus 4. Well, 3 times 4 is 12. We're expecting our answer to be on the positive side of the number line, so we're expecting it to be upwards. The minus in front of the 4 changes the direction once. 1 minus 1 changes direction, flips the direction we're travelling in. So we're heading down the number line, and it would then be a minus 12. We can now put those back together to find p. So p is the value of 7r, i.e. 35, plus the value of 3q, i.e. the minus 12. It's important we keep the minus 12 there. 35 plus minus 12, 35 plus, the plus does nothing to the direction we're travelling in. We're expecting to be travelling up, and the plus doesn't do anything to change that. The minus then reverses the direction of travel. So we're now going down. We're starting at 35, we're going down 12, so we're going to end up at 23. You could, of course, put all these into your calculator and do them carefully that way. 7 times 5 in your calculator, 3 times the minus 4 using the minus button on your calculator, which on my calculator is there. And then you could do 35 plus the minus 12, and you should still get the 23. Question 12. Here is part of a train timetable. So we've got Brighton and London, and then 3 trains listed. Train 1, Train 2, and Train 3. Graham gets to the station in Brighton at 7:15. Part A, work out how many minutes he has to wait until 7:22. So we're starting at 7:15, and then we're finishing at 7:22. We could just count on from 15 to 22, and we would find that that is 7 minutes. Part B, work out how long it will take the 0722 train to get to London. So we need to make sure we're looking at the right train first of all. We want the 0722 train, which is this one. So we start at 0722. We need to finish up at 9 o'clock. So why don't we start at 0722 and go on to the next hour? So the next hour will be 8. 22, well that's 8 minutes to past, and then another 30 minutes on from there, so 38 minutes. But it's not arriving at 8 o'clock, it's arriving at 9 o'clock, so 8 till 9 is another hour. So the total journey time, 1 hour and 38 minutes. There's nothing to say what form our answer needs to be in. We don't need to turn it into just minutes or anything. 1 hour 38 minutes is perfectly acceptable. Question 13. The diagram shows 9 identical squares inside a rectangle. The length of the rectangle is 12 centimetres. Work out the width of the rectangle. Now it looks like a really odd question, this. But actually it's simpler than it looks. Ignore the fact that there are squares all over this and they seem to be in some sort of odd pattern, 2 shapes not particularly connected. Ignore that. The fact that they are squares is important. We only know one thing about this rectangle, that it is 12 centimetres across. First thing, it's a rectangle, so we know that the width is not also 12 centimetres. Ignore the fact that these squares are all over the place. How many squares wide is the rectangle? Well, it's 1, 2, 3, 4, 5, 6 squares wide. And 6 squares cover 12 centimetres. That means then that 1 square must be 2 centimetres in width. 12 divided by the 6 is 2 centimetres wide. Now because it's a square, that means it must also be 2 centimetres tall. All 4 sides of a square being the same, after all. If the square is 2 centimetres tall, how many squares tall is the rectangle? Well, 1, 2, 3, 4, 5 squares in height. So the width then, to be 5 lots of the 2 centimetres, is 10 centimetres. Question 14. Write the ratio 4.5 to 2.25 in the form n to 1. So we're cancelling down ratios, but we are cancelling them down in a very particular way. 4.5 to 2.25, and we need to write that in the form n to 1. Well, n, remember, is a placeholder. N is whatever the value of that first number in this case needs to be so that the second number can be 1. We are specifically instructed not to cancel down to the simplest form necessarily, but to cancel down so that the second number is 1. The second number has to be 1. The first number, this n, is just a placeholder used to code for the number that needs to be there to make the second number 1. So then the question is, how do we get from 2.25 down to 1? Well, to get from 2.25 down to 1, we need to divide simply by 2.25. Anything divided by itself will give us 1. We are cancelling down this ratio. We're not cancelling it down to the simplest form, we are cancelling it down to a form that we are instructed to cancel it down to, but we are still cancelling down. Which means if we've divided by 2.25 on the right hand side, we also need to divide by 2.25 on the left hand side. So we could put in our calculator 4.5 divided by 2.25, and we would hopefully find the number that goes there is 2. So our ratio can be written in the form 2 to 1. Question 15. A garden is in the shape of a rectangle, 90 metres by 60 metres. Flowers are grown in 40% of the garden. The rest of the garden is grass. Work out the area of the garden that is grass. Key word in that question, one single most important word, is that word there, area, because that tells us exactly what to do. The rest of the garden is grass. Well, we know that the flowers cover 40% of the garden, so they must cover 40% of the area. The part of the garden that is not the 40% covered by the flowers must be the grass. So we need to start by working out the area of the whole garden so that we can then break it down in that kind of way. So step 1, we need to work out the area of the garden. How do we work out the area of a rectangle? Well, we take the 2 dimensions, we take the across and we take the up down, and we times them together. So we're going to do 90 times 60. We could pop that in our calculators and we're going to get that that is 5,400 metres squared. Metres squared because we've taken a metre length and we've times them together. Area dimensions are always given as units squared. Step 2 then. Well, we've got 2 options. We need to somehow work out the amount of garden that is flowers and then the rest being grass. We could either work out the 40% and then take it away and see what we're left with, or we could recognise that if 40% of the flowers are, or we could recognise that if 40% of the garden is flowers, then 60% of the garden must be grass, and we could find 60% of this and not have to take it away. Personal preference, they're both probably about as easy as the other. I'm going to go for the 40%. So 100% is our total amount of garden, 5,400. We could find a nice simple percent. We could break that down into 10%, say. If 100% is 5,400, then 10% we'll have to divide by 10 to find 10%, because 10 10% make up 100. We're dividing by 10, 5,400 divided by 10 is 540. We didn't want 10% though, we wanted 40%. So we would want 4 of those, and 4 lots of 540 will come to 2,160 metres squared. That's the amount that is flowers. So our final step then, I need to take the flowers away. 5,400 minus the 2,160 will leave me with 3,240 metres squared of grass. And again, as a reminder, you could recognise that if 40% of the garden is flowers, 60% of the garden will be the grass. If you found 60% of 5,400, you would also get 3,240. Question 16. 4 biased coins, A, B, C and D, are thrown. The probability that each coin will land on heads is shown in the table. So we have coin A, B, C and D, and then probability 0.33, 0.033, 1/3 and 30%. Notice at this point that the probabilities are given in 3 different forms. One of them is given as a fraction, as we're used to. 2 of them are given as decimals, as is perfectly reasonable because any fraction can be written as a decimal, and 1 of them is given as a percentage because of course any fractions or decimals can be written as percentages as well. A part 1. Which coin is least likely to land on heads? Well, we can talk about this kind of thing because the coins are biased. That means the chances of a head and the chances of a tail are not necessarily the same. The coin is weighted to one or the other. Which coin is least likely to land on heads? Well, it's going to be the one with the smallest probability. So the question is really saying, of these 4, which one is the smallest? Well, to be able to compare them, it would probably be helpful to have them all in the same form. So why don't we switch them all to decimals, since 2 of them are decimals already? And we have a calculator to help us. So we've got 0.33, we've got 0.033, we've got a third. We need to turn a third into a decimal. Well, we either just recognise that one because it's a standard fraction that it might be useful to have a decimal conversion for, or we could pop into our calculator, we could do the top number 1 divided by the bottom number 3. 1 divided by 3 comes 2, and if we use the S to D button to convert, 0.333333 and so on, 0.3 recurring. Remember, your calculator might show you 0.3 with a little dot above. It is important that you recognise it is 0.333333, not just 0.3. 0.333 ... And then we have 30%. Well, 30%, we can use that kind of pattern spotting. We could either recognise that it is 30 out of 100, 30 divided by 100 and do it that way, or we could do the pattern spotting and recognise that 30% will be 0.30 or just 0.3, and that's why it's important to recognise that a third is 0.3 recurring, not just 0.3, because a third and 30% are not the same. So we've converted all our numbers to decimals, we've got them all in the same form, we just need to pick the smallest one now. Well, they're all 0 points, so there's no comparison there. If we look at the tenths numbers though, we've got 3 tenths, no tenths, 3 tenths, or 3 tenths. The no tenths is going to be the smallest. So our smallest one is the 0.33, which means that B is the least likely to land on heads. Part 2 asks us which coin is most likely to land on heads. So very similar to that previous question, just asking us the one with the highest probability this time. So we need to look at those 4 numbers again. The 0.33, the 0.033, the 0.333 ... and the 0.3, and choose the biggest one. Well, again, they're all 0 points, so there's no information coming from the units of any use. We could look at the tenths though, 3, 0, 3 and 3. Well, clearly it's going to be one of the ones with 3 in and not this one, so it's not going to be that one. We've got 3 followed by 3. We've got 333 ... and we've got just 3 on its own. We're looking at the hundredths number. This has a 0 in the hundredth, so it's not going to be that one, it's going to be one of these two. And in fact, the very fact that this carries on, if we were to look at the next number along, there will be a 0 there and a 3 there. This one is going to be the biggest, so it's going to be C, coming from the 1/3. Julie says the probability that coin C will land on heads is the same as the probability that coin C will land on tails. Is she correct? Give a reason for your answer. Okay, when you think about a coin toss, there are 2 possible outcomes for a coin toss, ignoring the fact that the coin could land on its side because the chances of that are so small, we can pretty much ignore it. The coin will either land on heads or the coin will land on tails. That means if we take the probability of heads and the probability of tails, they should add to 1. So probability of heads plus probability of tails must equal 1. They must, because they are the only 2 possible outcomes, and the probabilities of all the possible outcomes will add to 1. We know that the probability of head is 1/3. Then the probability of tail must be whatever we need to add to 1/3 to get to 1. So the probability of a tail must be 1 minus 1/3 is 2/3. And that's possible as the coin is biased. So therefore, she is not correct. Probability of a head is 1/3, probability of a tail must be 2/3, so that those two probabilities can add to 1, as they should, because they are the only possible outcomes. So therefore, she is not correct. Coin B is going to be thrown 4,000 times. Part C, work out an estimate for the number of times coin B will land on heads. Keyword there is estimate. It will not necessarily land on heads this many times, but we can use the chance, the probability, to help us work it out. The probability of a head is 0.033. That means 0.033 of the time we will get a head, or we expect to get a head. Out of 4,000 throws then, we would expect 0.033 of them to be a head, i.e. 4,000 times the 0.033, so that we can scale, would be 132 heads. Expected. Again, doesn't mean that we would necessarily get exactly 132 heads if we were to throw the coin 4,000 times. We might get a few more, we might get a few less, but if we got wide of the mark of that, something is wrong with the coin. Question 17. There are 84 calories in 100 grams of banana. There are 87 calories in 100 grams of yogurt. Preeti has 60 grams of banana and 150 grams of yogurt for breakfast. Work out the total number of calories in this breakfast. What this question really is a ratio question. It's not necessarily immediately obvious how, but what we're doing is we're taking some information we know, we're rescaling it according to certain parameters, and then we are finding a total at the end. So I'm going to take the ingredients one at a time. I'm going to start off with the banana first of all. There's a couple of different ways you could write this. I'm going to write it as ratios. If you prefer to write it with equal signs, that's fine. If you wanted to do it in words, that would be fine. I'm going to use the ratio sign, and most of us seem to be fairly comfortable with that. I know that there are 84 calories to 100 grams of banana. Now I somehow need to get from that to there being 60 grams rather than 100. It's not immediately obvious how I'm going to turn 100 into 60. It's not like it's, say, half of it or a quarter of it. So what I'm going to do is I'm going to scale down, and then I'm going to scale back up again. I'm going to choose to scale down and work out how many calories there are in 10 grams. Because I could do that by simply dividing by 10. If I know that 100 grams is 84 calories, then 10 grams will be 10 times smaller. Now if I've divided by 10 on the right, I'm going to have to divide the number of calories on the left by 10 as well, and I'm going to find out that 10 grams contains 8.4 calories. Why is that useful? Because I can now use that to scale up to 60. 6 lots of the 10 grams will give me 60 grams. So 6 lots of 8.4 will give me the 60 grams worth of calories. I could do that on my calculator. I could do 6 times 8.4, and I would find that the answer there, once I've converted it to a decimal, is 50.4 calories. There is nothing that says in this question that the number of calories in total at the end has to be a whole number. It could well be a decimal. You can do the same for the yogurt now. We've started with 100 grams of yogurt. We need to find 150 grams worth. I could do the same kind of thing as I did above, although actually this one I could do in a much simpler way. 87 calories in 100 grams. Now I need to get up to 150 grams. That needs an extra 50 grams worth of yogurt. Well, 50 grams is half of 100 grams. So I should be able to work out how many calories there are in 50 grams fairly easily. Because I would just need to divide my 87 by 2. So I could do 87 divided by 2, pop that into the calculator and get 43.5. 43.5 calories in the 50 grams then. What can I now do with those? Well, I know how many there are in 50. I know how many calories there are in 100. I could just add them together to get the 150. So I could add those together to find that there are 87 plus 43.5 is 130.5 calories in 150 grams. My final step then, for if the bananas were step 1, the yogurts were step 2, my step 3, I need to work out the total number of calories in the whole breakfast. So the total number of calories would be 50.4 plus the 130.5 would be a nice total of 180.9 calories. Question 18. Machine A and Machine B both make car parts. Machine A makes 6 parts every 10 minutes. Machine B makes 13 parts every 15 minutes. On Monday, Machine A makes parts for 12 hours. Machine B makes parts for 10 hours. Work out the total number of parts made by the two machines on Monday. Actually, stylistically very similar to the previous question, the idea of taking some certain starting pieces of information, scaling them up or down, and then putting them together at the end. We can take the machines one at a time. So we can start with machine A. We could work out how many parts machine A makes for the whole of Monday, and then we could work out how many parts machine B makes for the whole of Monday, and then put them together at the end. So machine A, let's take the two bits of information that we have about machine A. Machine A makes parts. It makes 6 parts every 10 minutes, and it makes parts for 12 hours. So we need to work out how many parts it makes in the 12 hours. Well, let's first of all start by working out how many parts it makes in 1 hour. Machine A, 6 parts in 10 minutes. We want to work out how many it makes in an hour, then we need to work out 60 minutes worth. 60 minutes worth. Well, that's 6 lots of 10 minutes. So it must do 6 times 6 is 36 parts in 60 minutes, i.e. 1 hour. So 36 parts in an hour. Machine A makes parts for 12 hours. So it will make 12 lots of 36 parts. 12 times 36 in our calculators, 432 parts in 12 hours. So on Monday, Machine A makes 432 parts. Machine B now. Let's pick out the two bits of information we have for Machine B. Machine B makes 13 parts every 15 minutes, and Machine B makes parts for 10 hours. So if Machine B makes 13 parts in 15 minutes, we can still do the same kind of thing. We can scale up to an hour, and then we can scale up to 10 hours this time. Well, we want 60 minutes for an hour. There are 4 lots of 15 minutes in an hour. 4 15s make 60, so we need 4 times 13 is 52 in 60 minutes, which is of course 1 hour. So 52 made in an hour. Machine B makes parts for 10 hours, so therefore we have 10 lots of 52 is 520 parts in 10 hours. Final part of the question then, the total. Well, if Machine A makes 432 and Machine B makes 520, if we add those together, we can work out our total, 952 car parts. Question 19. Here is a plan of a kitchen drawn to a scale of 1 to 30. And then we're reminded of the scale underneath 1 to 30. Sam is going to put a small table in the kitchen. The table has to be more than 180 centimetres from A, more than 150 centimetres from BC. Show by shading on the diagram the region where Sam can put the table. Now the presence of this diagram plus the scale plus the information underneath this more than a certain distance from somewhere, more than a certain distance from somewhere else, this kind of setup suggests to us that it's a constructions question. So we're going to have to use those different constructions that we've got. We're going to have to work out first of all which one it is, what we need to draw, and then put it all together to work out the information at the end. I'm going to start off by noticing this scale. The scale is that 1 to 30. There are no units given on that scale, notice. That means that one something on the diagram is 30 of the same somethings in real life. We're likely to be measuring on the diagram in centimetres. So every 1 centimetre we draw on the diagram is 30 centimetres in real life. That means if we want to mark 180 centimetres in real life, we need 30, 60, 90, 120, 150, 180. 6 centimetres on the diagram. And for the second instruction, we need to mark 150 centimetres from BC. Whatever we're drawing, it's going to be something to do with 150, 30, 60, 90, 120, 150. 5 centimetres on the diagram. So whatever we're drawing something to do with 6 centimetres for the first and something to do with 5 centimetres for the second. I'm going to grab 2 things to help me with this question. I'm going to grab my ruler, I'm likely to need it, and I'm probably, if it's a constructions question, going to need this somewhere. Already set up, I'd set it up before the exam notice. End of the pencil and the end of the compass, exactly aligned. I've done that carefully. That's why I've done it in advance, so that I can take my time to line them up carefully and make sure it's as accurate as it can be. Because the key with these questions is accuracy. I'm going to do the instructions in order this time. I'm going to start with the first one, the more than 180 centimetres from A. A is a single point. Now we want a given distance away from a certain point. Distance away from a point means we are talking about this kind of loci idea, this sort of region enclosed around a certain point. And if it's around a certain point, we are effectively drawing a circle, because we need all of the points that are within 6 centimetres of A in any given direction. So we're going to be drawing a circle of 6 centimetre radius. So I'm going to put my point of the compass at the 0 on the ruler, and I'm going to open the compass until I get to 6 centimetres with the pencil. I've now set that compass to a 6 centimetre radius. I'm going to place the point of the compass quite firmly into the paper at A. I'm going to hold my compass very carefully. I'm only going to hold my compass on the top bit there. And I'm going to draw a nice sweeping circle around A. Except I don't really need to draw a circle, because there's 2 walls of the kitchen there. There's the wall here, and there's the wall here. So really, I'm only actually drawing a quarter of a circle. I am drawing a circle, really. It's just that the circle is bounded by the walls of the kitchen. So anything on this circular line is exactly 6 centimetres away. Now I wanted, eventually, more than 180 centimetres in real life, i.e. more than 6 centimetres on the diagram, away from A. So I need to be outside the circle somewhere. Everything on this line is exactly 6 centimetres away. Everything within it is less, and everything outside it is more. And I needed more than the 6 centimetres, the 180 centimetres in real life. The second instruction given to us is that we need to be more than 150 centimetres, i.e. 5 centimetres on the diagram, away from BC. Now BC is not a single point, it is in fact a line. But actually we are still talking about the same kind of idea. We are talking about a region in space, this time around a line. And a region around a line is that running track shape, that kind of this sort of shape. But because we've got the other kitchen walls here, we've only really got the top part of this shape. We just need to be within 5 centimetres of that wall, that whole line. So I can just measure 5 centimetres out at the bottom, maybe measure 5 centimetres out at the top as well, just to check. And then join them up with a nice straight line. Anything on the right of this line is less than 150 centimetres, 5 centimetres in the diagram, away from this wall. Anything on the left of the line is more than 150 centimetres, 5 centimetres in the diagram, away from the line. So the final step is to put those 2 bits of information together to work out where I need to shade. There are 1, 2, 3 clear regions. I need to work out which one I'm shading. Well, we said before I need to be outside the circle, because I need to be more than 180 centimetres away. The circle is 180 centimetres away, and I need to be more than that, so I'm either this one or this one. I also need to be more than 150 centimetres from BC. If I need to be more than this line, well, this line is 150 centimetres away, I need to be more than that, so I need to be on this side of the line. So I need to shade in this bit in the middle here. And this shaded bit here is my region where I could put the table. 4 marks available for this question, presumably 1 mark for showing that you can deal with the scale and getting either the 6 centimetres or the 5 centimetres correct. 2nd mark coming from the circle, 3rd mark coming from the line, and 4th mark coming from interpreting the information correctly to get the shaded region. Question 20, Part A. Solve 14n is greater than 11n plus 6. So first of all, ignore the fact that that is an inequality and concentrate on the word solve. Solve means we need to find the value that the unknown letter is coding for, in this case the n. With this being an inequality, however, we're not just going to get n equals something, we're going to get n in relation to something else. N is greater than something or n is less than a certain value. And we need to work out what that value is. Solving inequalities, however, is exactly the same as solving equalities. And in fact, we cheat it. And our very first step is to say, let's ignore the fact that it's an inequality and let's solve it as if it was an equals. So we're going to change the question first of all. We're not going to solve this, we're going to solve instead 14n equals 11n plus 6. We're going to swap the sign, whichever inequality sign it is, for an equals sign. In doing that, we can solve the equality in the way that we normally would for any equation of that type. And then we can swap the sign back at the end. So to solve an equation of this type, this is not a function machine type question, this is a scales type question. We know that because we've got the unknown on this side and on this side. We've got n's on both sides of the equals. The unknowns being there on both sides of the equals means we've got to do this balancing scales kind of thing. So I'm going to set my balancing scales up first of all, and I'm going to draw them carefully. So on the left-hand side of the scales, I'm going to give myself 14 n's. So there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14. That is my 14 n's on one side of the equation. On the other side, we need to have 11 n's, and then we need to have a plus 6. 11 n's, and I'm going to have the plus 6 there as well. Now those two sides of the scales are balanced, and the idea is to leave them balanced all the way through. I'm going to put an equals in the middle to show that they are balanced. We need to keep these balanced all the way through, whatever we do to them. So there are 3 things we can do to keep those scales balanced. We can either do absolutely nothing to them at all, which seems a little bit pointless. Alternatively, we could add the same amount of information onto both sides. As long as we put the same on one side as on the other, they are staying balanced. Or we could take the same information off both sides. Now that third one is the ideal. The problem is that we've got n's on both sides. If we can reduce this problem to one where we've just got n's on one side or the other, then we can solve it. We can solve it with a function machine. So we need to try and get rid of n's. So we need to ask ourselves one simple question. We need to ask ourselves, is there stuff on both sides that we can get rid of? If there is stuff on both sides that we can get rid of, that's the direction we should go in. If the answer to that question is no, then we're going to have to go down the route of adding the same things onto both sides. But when we ask ourselves that question for this, is there stuff on both sides that we can get rid of? Is there stuff that's on both sides? Well, yes, there is. There are n's here and there are n's here. So we can get rid of n's. We can try and get rid of n's until they've all gone on one side. So I'm going to go through and I'm going to cross them off. I can cross 3 off that side, for example, and as long as I cross 3 off the other side, then it's still balanced. I could take another 3 off both sides, and it's still balanced. I could take another 3 off, and it's still balanced. And I've got to be careful at this point. I could take 1 off there and 1 off there, and it's still balanced. I could take 1 off there and 1 off there, and it's still balanced. I could take 1 off here, but I wouldn't have 1 to take off here, so it wouldn't be balanced anymore if I did that. That means that this is as far as I've gone. On this side, we are left with 1, 2, 3 n's. On this side, we are left simply with a plus 6, which I'm just going to write as 6. These two things are equal. We know they're equal because the scales are still balanced. 3 n's on this side and a plus 6 on this side. Remember that it doesn't matter how many blocks are there, it matters what is there. It's not the number of things, it's what they actually are and the values. 3 n's then are the same, are balanced with the plus 6, so they must be equal. At this point, I can rule off under here. I don't need to look at these scales again. All I need to do now is solve this new equation we've ended up with, the 3n equals 6. That's now a function machine question. It's just a single value. It's just a single. That's now a function machine question. It's just got n's on this side and a number on the other side, but it is still a function machine question. I'm going to start with the n. First thing we do to it is we times it by 3, and that spits 6 out the end of the machine. Reversing it then, the 6 goes back in. We would divide by 3 this time instead, meaning we will get 6 divided by 3 is 2. Now that means that if we were solving the equality, we would get down to n equals 2 at the end. But there is one final thing we need to do. We were not solving 14n equals 11n plus 6. We were trying to solve 14n is greater than 11n plus 6. When we solved the equality, we got n equals 2. We need to solve the inequality, so all we need to do is swap the sign back at the end. I'm going to put exactly the same sign back in, because nothing changed sides any of the way through. I'm going to put the same sign back in at the end, and we're going to say that n greater than 2 is our solution to that. I could even check that it works. Well, we could check it with the 2. When we have 2, we have 14 times 2 is 28, and on the other side we have 11 times 2 is 22 plus the 6. Okay, good, that's 28. So when we test it with 2, we do get 28 on both sides. We're expecting anything greater than 2 to work. So let's pick 3, say. 14 times 3. Well, 14 times 3, popping that on our calculator, is 42. On the other side, though, we have 11 times 3 is 33, plus the 6 is 39. 42 is bigger than 39. I would say that's true, so that works. We could also test if we wanted something that is less than 2, because this shouldn't work. If we test something that's less than 2, well, let's test 1. We get 14 times 1 on this side is 14. On the other side, 11 times 1 is 11. 11 plus 6 is 17. 14 greater than 17. Well, no, that doesn't work. But that's good, because it's not supposed to. Only values of n bigger than 2 are supposed to work, and we've just checked, and it does work. Part B, on the number line below, show the set of values of x for which minus 2 is less than x plus 3 is less than or equal to 4. Now this looks a little bit odd. It's clearly a between kind of idea, that this x plus 3 is between minus 2 and 4. Including the 4, because we've got this little line underneath there. So not including the minus 2, but including the 4. Problem is, though, I need to show on the number line the set of values of x. And we've got what x plus 3 is between. So we need to muck about with the inequality a little bit first. We need to change it so that it's showing us information not for x plus 3, but for x. Now what's happened in the middle of this inequality is we've taken our x and then we've added on 3. And when we've added 3, the smallest it could possibly be was minus 2. Now that means before we added the 3, the smallest it could have been must have been minus 5. When we put the 3 on, the smallest value it could take was minus 2. Before we added the 3, it must have been minus 5. So the smallest that x could have been was minus 5. So that then when we add the 3, we get up to the minus 2. The biggest that x plus 3 could be is 4. But that's the biggest that x plus 3 could be. Before we added the 3, the biggest it must have been was 1. So if x plus 3 is between minus 2 and 4, then x must be between minus 5 and 1. 3 less on the smallest and 3 less. So if x plus 3 is between minus 2 and 4, then x must be between minus 5 and 1, 3 less on the smallest value and 3 less on the biggest value. So now we just need to draw this inequality on the number line. So I need to first of all mark on the end points. I need to mark on the minus 5 with a circle. I need to mark on the 1 with a circle. The minus 5 I'm going to leave as an open circle because we're not including the minus 5, just like we weren't including the minus 2 up here. The 1 I am including because I was including the 4 up here, so I'm including the 1 here. So I'm going to colour in that circle. I'm going to shade that one in to show we're including the 1 endpoint. All I need to do now then is draw a straight line between the two. I'm going to do this with a ruler to keep it neat, but you could probably freehand it as well. So we're then showing that x is between -5 and 1, including the 1 but not including the -5. And a reminder that first of all we mucked about with the inequality because we needed to show the values of x, not the values of x plus 3. I suspect if you had drawn -2 to 4 on the number line and got the circles correct, you'd probably have got 1 mark because you have shown that you can draw an inequality on a number line. If you changed the inequality, as you should have done, then you would probably get the full 3 marks. Question 21. On the grid below, draw the graph of y equals 2x minus 3 for values of x from -2 to 4. Classic sort of graph question. We've got a grid given to us with our coordinate axes on them. We are given an equation of a graph, y equals 2x minus 3, which hopefully you will notice is a straight line graph. It's got this mx plus c form. Y equals a certain number of x's plus or minus a certain number on the end for values of x from -2 to 4. Now there's lots of different ways we can go about this question, lots of different things we can use to help us find the information we need. What we ultimately need is we need a set of coordinates to plot on that grid, defined by this particular equation. So what we're going to do is we're going to draw ourselves a table. We're going to have values of x and y. The values of x, remember, are our inputs. We choose those, except we don't really. They are from -2 to 4. So we need -2, -1, 0, 1, 2, 3, and 4. And what we're going to do is we're going to plug them through the equation, through the rule that generates these points. We're going to get an output value for each one. So we're going to work out an output y value for each one of those to give us pairs of coordinates. We're effectively going to substitute each of these values of x into the equation one at a time and work out the output that's obtained. Except we don't necessarily need to do that. We can use clues and hints to help us along the way. First hint that we have. The number at the end is where we cross on the y-axis. That means the value of x, on the y-axis is 0 because we've gone 0 spaces along. Point of that is when we substitute x is 0 in, and we can check this, the rule says y is 2 lots of our x and then take away 3. 2 lots of 0 is 0 and then take away 3 is the -3. So the number at the end is the value of y when the x number is 0. So we can fill that one in straight away. We could work out the value of y when x is 1 now. 1 is a fairly easy number to work with. So our rule says we take our x value, in this case 1, we times it by 2, and then we take away 3. So we're going to do 2 lots of 1 is 2, and then take away 3, -1. And we're going to at this point notice something. -3 to -1 is a jump of 2. Well, that makes sense. We should have been expecting that because the number in front of the x is a 2. Our output values will go up in jumps of 2. So the next one up will be 1, 3, and 5, and going down the other way, -5 and -7. If we were to work out each of those inputs and output pairs individually, we would still obtain the same values. 2 lots of 4, for example, is 8, and then take off the 3 does indeed give us 5. They are our input and output pairs. So what we're going to do is we're going to plot them as coordinates on our grid. We're going to match up an x with an output y. Hopefully we are going to end up with points that are in a straight line. If we don't, it's a big clue that we've done something wrong. -2, -7. Okay, -2, -7 there. -1, -5. So we're going to go across to the -1 and down to -5. 0, -3. So we're across to 0 and down to -3. This is looking good so far. 1, -1. So that's there. 2, 1. 3, 3. Across to 3 and then up to 3. And 4, 5. Across to 4 and then up to 5. And that's looking pretty good. The other thing it's worth bearing in mind. You only really need 2 points to draw a line. 3, I guess, to be sure that you've got the right one. This one is easy to work out. This one was easy to work out. You could plot those 2 on the grid. That's here and here. You could then probably work out another one just to be sure. but you could always draw the line and then work out the coordinates. You could work out the pairs of input and output after that. So a nice smooth straight line through those points. However you do it, it doesn't matter, but you should end up with this diagram and this table at the end. Final thing we should do, should probably label the curve just to make sure we know what it is. Y equals 2x minus 3. Doesn't really matter so much for this question, but it's good practice anyway. Question 22. Hannah is planning a day trip for 195 students. She asks a sample of 30 students where they want to go. Each student chooses one place, and the table shows information about her results. So we've got 4 places: theme park, theatre, sports centre and seaside. And we've got 10, 5, 8 and 7 students respectively. Part 1. Work out how many of the 195 students you think will want to go to the theme park. Now the idea with this is sample sizes, scaling up to be representative of a whole. Hannah has not asked all 195, she has asked 30. And we're going to focus on those 30 first of all. We're looking at the theme park, so we're looking at this row here. 10 out of 30 students want to go to the theme park. 10 out of 30, if we write it like that, we will hopefully notice will cancel down to become a third. Divide top and bottom by 10, 10 out of 30 is the same as a third. If a third of the sample size want to go to the theme park, it might be reasonable to assume that a third of the total number of students, that's a third of the 195 students in total, will also want to go to the theme park. That's the idea of picking a sample size. Rather than have to ask everybody, you just ask a certain group, a certain chunk, and assume that those results will hold for everybody. So we need to work out a third of 195, i.e. on our calculators we're going to do 195, we're going to split it into 3, we're going to divide by 3. And that will give us 65. So it will be reasonable to assume that around 65 of the overall students will want to go to the theme park. Now, of course, that is just an assumption, and in fact, Part 2 asks us about that. Part 2, state any assumption you made and explain how this may affect your answer. Well, we're assuming that because a third of the sample size want to go to the theme park, then a third of all of the students, Well, we're assuming that because a third of the sample size want to go to the theme park, a third of the 195 students also want to go to the theme park. We are assuming that the 30 students, and you can get a buzzword in here, are representative of the whole sample, the whole group. We are assuming that the 30 students are typical students, assumes that they are not more likely to pick one thing than the other. It assumes they've been chosen at random. It assumes that they represent, that their views, that the 30 students' views are very similar to the 195 students' views, just on a much smaller scale. In fact, the true number, and this is the and explain how this may affect your answer, the true number may be higher or in fact lower than 65. If you pick a different group of 30 students from the 195, you might get a different answer. You might get 60. You might find that there's 80. We don't know. Depends how representative the 30 students are of the 195. Question 23. A container is in the shape of a cuboid. So it's 30 centimetres across the bottom, 6 centimetres in depth, and then 19 centimetres in height. The container is 2/3 full of water. A cup holds 275 millilitres of water. What is the greatest number of cups that can be completely filled with water from the container? Okay, so we're talking about liquid inside a cuboid container. we are talking then about the amount of stuff that can fit inside it. And if we're talking about the amount of stuff that can fit inside it, we must be talking about the volume. So the first thing we need to do is we need to work out the volume of this cuboid. So to work out the volume of any 3D shape, we find the area, first of all, of the front face. We notice that that is a prism. It is the same shape all the way through. We find the rectangle at the front, find the area of that, and then stretch it back into 3D space to make it into a volume. So the area of the front, well, the area of the front is going to be 30 centimetres across times the 19 centimetres in height. 30 times 19 on our calculators, 570 centimetres squared, because we're still dealing with an area at this point. We didn't want the area though, we wanted the volume, so we need to stretch that 570 centimetres squared back by 6 centimetres worth. So 570 times the 6 there will give us our volume of 3420 centimetres cubed. Now we're told that the container is 2/3 full of water. So we need to work out how much water can go in there in terms of centimetres cubed. We're not going to fill it, we're not going to have 3,420 centimetres cubed, we're only going to have 2/3 of that. So our step 2 then. Well, I could find 1/3 easily enough. 1/3 of 3420 by dividing by 3. 3420 divided by 3 will give me 1,140 centimetres cubed. But I didn't want 1/3, I wanted 2/3. So 2/3 then. If I double that number, if I have 2 lots of the 1,140, 2,280 centimetres cubed worth of water. Probably 2 marks up to this point, because the next one requires a logical leap that not everybody would necessarily realise you could make. And actually there is no reason why you would necessarily be expected to know this, but it turns out, and you could probably have a good guess at this, even if not. We are dealing with centimetres cubed here. But the amount of water being talked about is in millilitres. Now it turns out that actually millilitres and centimetres cubed in terms of liquids are in fact equivalent. I'm not saying that millilitres and centimetres cubed are the same. They are different measures, they are for different things, but they are equivalent. We have, in fact, that 1 millilitre is the same as 1 centimetre cubed. Do I think this is a slightly tricky logical leap to make? Yes, because there is no reason why you necessarily should know that. But it turns out that it is the case. At the same time, if you only get to here, you're probably getting 2 marks. And 2 marks out of 4 is much better than none. This has nothing to do with the millilitres being used. This is just talking about volume and some fraction stuff. If, however, you did know that 1 millilitre is 1 centimetre cubed, or you could make that logical leap, or you could just kind of have a guess from the question, 1 millilitre is 1 centimetre cubed, so we could just say that there are 2,280 millilitres worth of water that we could put in glasses. So we could say that there are 2,280 millilitres of water in the tank. But now we need to work out how many cups we can fill. So we're going to take out 275 mils, and then another one, and then another 275, and another 275, and we're going to keep going until we've not got enough left to do. So I need to work out how many 275s there are in 2,280. So I'm going to do 2,280, I'm going to divide it by 275. And when I do that, I'm going to get 8.2909 ... 8 and a bit. So the greatest number of cups that I can fill, because that's what the question's asking me for, must be 8. The greatest number of cups I can fill is 8 full cups with a little bit left over. And in fact, if we wanted to check that, 8 times 275 is 2,200. We've got 80 millilitres left over, but that's okay, because we're asked for the greatest number of cups that we can fill. Question 24. ABC is a right angled triangle. Calculate the length of AB. That's this side here. Give your answer correct to 2 decimal places. Now there's something interesting about this question. We're talking about right angle triangles, we're talking about angles, we're talking about sides. You might be starting to think, oh, well, it's talking about sides of a triangle. Well, maybe we're looking at something like Pythagoras with the boxes on each side. Trouble is, we've only got one side given to us there. For a Pythagoras question, we'd have to have two, so that we could then work out the third. The fact that this has an angle in as well means that this is something called a trigonometry question. And you might well be sat there thinking, I've never heard that word before. No, you haven't. Because trigonometry is one of two topics that I decided not to bother teaching, for the simple reason that there is one trigonometry question that's going to come up on that exam somewhere. And this one is worth 2 marks. Trigonometry would take a whole lesson to teach, and a whole lesson for 2 marks. And I'm going to be honest, it's not an easy topic anyway. It's proper high-level stuff. It's the hardest thing on the foundation paper. If it's a triangle question and we're talking about just sides, no angles mentioned, then it's a Pythagoras question, you can do it. If it's a triangle question and it's just talking about angles, it's probably an angle rules question and it's fine, you can do it. If it's got a mix of angles and sides, it's a trigonometry question and we're not going to bother. For the simple reason that it's more work than it's worth to get a couple of marks, 2 marks, 3 marks at most. It will turn up once, worth skipping. Question 25. Sally used her calculator to work out the value of a number y. The answer on her calculator display began 8.3. Complete the error interval for y. Now, error interval is another of those words that we've not really come across, but there are clues. In fact, if we look at the answer line, there is a big clue there. Y is between 2 things. So y is bigger than something and smaller than something. Error interval is just a fancy way of saying if the calculator starts 8.3 and then will continue to be something else, what's the absolute smallest it could be and what's the absolute biggest it could be? An error interval is just a fancy way of asking that question. Well, the very smallest that it could be is just 8.3 with nothing else after it. That is the very smallest that it could possibly be. So the very smallest is that it is actually just 8.3 and there's nothing after it. Or perhaps there's an 8.30 after it. And that the very smallest it could possibly be is 8.3. And it could be 8.3. But maybe it's 8.30 and then something else. So maybe it's 8.31, 8.32, 8.33, 8.34, 0.35, 0.36, 0.37, 8.39. But then maybe it's not just 8.39, that's not the biggest. Because maybe it could be 8.399, or 8.3999, or 8.3999999 and so on. Well, 8.3999999 is very, very, very close to 8.4. So it could be so infinitesimally close to 8.4, never actually being 8.4, because the calculator display definitely begins 8.3, but it could be just smaller than 8.4. And that's why this inequality sign does not have the line underneath it. So it could be just smaller than 8.4. So y has to be between 8.3 and 8.4, but not actually being 8.4. Question 26. £360 is shared between Abby, Ben, Chloe and Dinesh. The ratio of the amount Abby gets to the amount Ben gets is 2 to 7. Chloe and Dinesh each get 1.5 times the amount Abby gets. Work out the amount of money that Ben gets. So it's a ratio question. We know it's a ratio question because we've got this ratio 2 to 7 given to us. We're going to share £360 between 4 people and we only have ratio information for 2 of them. It would surely then be much more helpful if we could find a ratio including all 4 people. An A to B to C to D ratio, where we already have that A to B is 2 to 7. Well, if we could work out what numbers go here and here for C and D, then we'd have a 4-way ratio and we could split the £360 by those 4 numbers. Well, how can we work out that? Chloe and Dinesh each get 1.5 times the amount that Abby gets. Well, Abby gets 2 shares. Chloe gets 1.5 lots of 2. She gets 1.5 times that 2, i.e. 3. And Dinesh also gets 1.5 times Abby's share, so he also gets 3. So our ratio now is 2 to 7 to 3 to 3. And the question becomes, share £360 in the ratio 2 to 7 to 3 to 3. And at that point it's a standard ratio question. So we're going to have £360 in a pile on the table. We're going to take 2 out, give it to Abby. We're going to take 7 out, give it to Ben. 3 for Chloe and 3 for Dinesh. And then we're going to do it again. 2 and 7 and 3 and 3. And 2 and 7 and 3 and 3. And each time we're doing that, the amount of money that we're taking out to split between the 4 of them is 2 and 7 and 3 and 3, i.e. £15. We're taking £15 out, we're giving 2 to Abby, 7 to Ben, 3 to Chloe, 3 to Dinesh. So if we're taking £15 out each time and splitting it in those 4 different ways, how many times can we do that before there isn't any left? We're going to keep taking the 15 out until there isn't any left. Well, we can do that. 360 divided by 15 is 24 times. So 24 times we can take £15 out and we can share it among the 4 of them. If we do that sharing 24 times, then that means that Abby gets 24 lots of £2 and she gets £48. It means that Ben gets 24 lots of £7 and he gets £168. It means that Chloe gets 24 lots of £3 and she gets 72. And it means that Dinesh also gets 24 lots of £3 and he also gets 72. At this point it might be helpful to check that we've got all £360 of the money accounted for. So 48 plus 168 plus 72 plus 72 does indeed add to 360. The chances of us getting it wrong, but the numbers still working out to add up at the end, very, very slim. We just need to check what we need to give. Do we need to give all 4 or do we just need to give certain numbers of them? Well, we need to work out the amount of money that Ben gets, and Ben gets £168. Question 27, Part A. Write 0.00562 in standard form. So clearly a standard form question. Well, with standard form what we need to do is we need to write something as a certain number times a power of 10. The number has to be between 1 and 10. Not including 1 and not including 10. So it has to be bigger than 1 and less than 10. So we need to choose, first of all, something that looks a bit like this, that keeps the numerical information, but is between 1 and 10. And clearly that something is going to be 5.62. It's the only way to keep this and rescale it so it's instead between 1 and 10. And I'm going to first of all write that in a hundreds, tens and units grid, 5.62. And then underneath, I'm going to write down the number that we actually started with. So that's 0.00562. And I'm going to count how many jumps we need to go to get this one to this one. Doesn't matter which number I pick. If I pick the 2, for example, it needs to go 1, 2, 3 jumps. And everything else will also go 3 jumps. 1, 2, 3 jumps. 1, 2, 3 jumps until it ends up where it originally started. So, 5.62, there's our number part. We need the times 10 to a certain power. The power is going to be something to do with 3. Bear in mind though that this is a small number. It's had to go 3 jumps down the hundreds, tens and units grid to get smaller. If it's gone down or got smaller, if it's a small number, our power needs to be -3. Part B, write 1.452 times 10 to the 3 as an ordinary number. Other way round this time then. So we're going to start with the 1.452. So units and tenths, hundredths, thousandths. So we need to instead now move this number 3 jumps up the grid. So the 1 is going to move 1, 2, 3 jumps into the 1,000. It's going to get 10 times bigger, then 10 times bigger again, then 10 times bigger again. That's 3 jumps in the hundreds, tens and units. The 4, the 5 and the 2 are going to be dragged along with them. So the 4 is going to end up in the hundreds, the 5 in the tens and the 2 in the units. Do we need to fill anything out to make it a proper number? Well, no, we don't, because it's already filled up to that decimal point, 1452, and there is our answer. And I could let you in on a little secret. With this particular one, not necessarily with all of them, but with this particular one, if you were to put this in your calculator, 1.452 times 10 to the power of 3, using that times 10 to the x or the EXP button at the bottom. Some calculators, but not all. Mine will. If I press equals, will just give me the answer 1,452. Easy mark. With the standard form questions, particularly if they're on a calculator paper, always worth checking whether your calculator will do it for you or not. If your calculator will do it for you, it wouldn't for the first one, but it does for this second one. If your calculator can do it for you, have your calculator do it for you. Question 28. Here are the first 5 terms of a Fibonacci sequence. 3, 3, 6, 9, 15. Part A. Write down the next 2 terms of the sequence. And I imagine you are quite reasonably saying, well, what's a Fibonacci sequence? If you know, great, good, nice easy question. If you don't, it's not that difficult to do. You could probably try and work it out. With any sequence, knowing what the pattern is doing is the key to unlocking the sequence. Is it going up in a certain number? Is it going down in a certain number? Is there some other connection between them? Well, let's have a look. 3 to 3, no change, so we're adding on 0. 3 to 6, we're adding 3. 6 to 9, we're adding 3. 9 to 15, we're adding 6, and that should be enough to recognise what's going on with this sequence. Focus on the 3, and the 6. Do they look at all familiar? Well, yes, they do. It's the sequence above. 3, 3, 6. So the next jump, well, 3 and 3, 3 and 3, 6 and 6, the next jump would be adding on 9. The jumps are the sequence again, with this double number at the front, this adding on 0, to allow this to be possible. So the next jump would be adding on 9. So we do 15, add 9, and that would take us to 24. So the next number would be 24. The next jump up would be 15. So we'd be doing 24 plus 15, because the next number in the original sequence was 15. Again, the jumps are the sequence repeated. 24 plus 15 is 39, and the next number in the sequence will be 39. Now, if we've worked that out, we've then worked out what a Fibonacci sequence is. That might help us for the next part of the question. The first 3 terms of a different Fibonacci sequence are A, 2A. Find the 6th term of this sequence. So it's an algebra sequence this time, rather than a numerical one, but the pattern still works in the same way. Fibonacci sequence, the jumps are the sequence repeated. So our first term is A, our second term is A, and our third term is 2A. We could look at the jumps. It's gone 0 and then A. The jumps, remember, are the sequence again. So we can ignore the 0. That lets it all work. That shifts it along. First jump was A. So the second jump will be the next thing in the sequence. The second jump will also be A. So the next jump will be the next number in the sequence. The next jump will be A. So we're going to go 2A plus an A gives us 3A. And the fourth term will be 3A. The next jump, the next thing in the sequence, so we've gone A, we'll be adding on 2A now. And we're going to have 3A plus 2A is 5A. So the fifth term will be 5A. The next jump, A, 2A, 3A will be the next jump. 5A plus 3A, and the sixth term will be 8A. Tricky question because of this use of the word Fibonacci. No real reason why you would necessarily know what that is, but you could probably try and work it out from the pattern. As with any sequence, look at the pattern, see if there is a link. There is always going to be a link for it to be a sequence. Final question, question 29. We've got 2 column vectors. A is 4, 5, and B is 3, 2. And we need to work out A minus 2B as a column vector. Column vectors then. Directions 4 across and 5 up. 4 to the right, in fact, and 5 up. 3 to the right and 2 up. So we're going to do A is 4, 5. And then we're going to do 2 lots of B, which is 3, 2. We could work out the 2 lots of B first of all. If we do B twice, we go 3 to the right and then 2 up, and then 3 to the right and then 2 up. That is an overall movement of 6 to the right and 4 up. So we've just doubled the 3 and doubled the 2. So now we can look at the across directions first. We're going to go 4 across, 4 to the right, and then we're going to take off a 6. We're going to go back, in fact. 4 take away 6 is -2. And then on the bottom we're going to go 5 up, and then we're taking off going 4 up. So 5 up less 4 up is in fact only 1 up. So our final answer then, A minus 2B as a column vector will be -2, 1.